Having lunch. We are beginning, but we are very sure the speakers are very loud, so you can hear us, but we encourage you to quickly join us down here. So, ladies and gentlemen, now we continue to the training workshop, and we started with the introduction to roadway network components. We had our coffee and tea break. Then we went into parameters impacting road network conditions, resilience, and sustainability. The opening ceremony, we all enjoyed our lunch. If you enjoyed your lunch, can you please wave your hands? Yes, that is to give you energy to enjoy the other parts of the training. So now we shall dive into history of pavement design. Okay, history of pavement design theories and their impact on roadway conditions. Once again, we have the lead instructor to take us on this course, Dr. Amin Aknok. He is a professor of construction engineering and management at East Carolina University, North Carolina, USA. Can we please put our hands together to applaud him? Thank you. So, Doctor. Okay, let me get it.
Okay, good afternoon everyone. Enjoyed the lunch? So, are you ready for more, or everybody's heavy and wanting to sleep? Excellent. So, yeah. You know what? The camera is in my line of sight, you know? So we will continue this session. I mean, the majority of this set of slides can be done today. I mean, hopefully we can finish it, but if not, the very last few ones will be relevant to SuperPave, so they can fit also on tomorrow's early morning presentation. So here, basically, I will be telling a quick story about the history or the background, how asphalt came into play and how it was entered into the business of the roadway or roadway construction in the US and the rest of the world, and why the flexible pavement, which is, you know, asphalt concrete pavement, is having the lion's share. As I said before lunch, in the US it's 93% of the roadway network in the US is being constructed using asphalt pavement, and there are 4 states that already has absolutely zero asphalt, zero concrete on them, and more than 90% of the states have got a huge percentage that increased 90% of its roadways. Remember, the roadway network, we're talking about 4 million or close to 4 million miles or 6.5 million kilometers. So if you think about the business of asphalt, it is a huge one. Together with concrete, they form the vast majority of the construction industry. And to put things into perspective, the construction industry represents 9% of the GDP of the United States. So we're talking about 9% of 24 trillion US dollars. So we're talking about 2.1 or 2.2 trillion US dollar dedicated to the construction industry and more than 70% of this is dedicated to both asphalt and concrete construction. So you can think of how the magnitude of the business of asphalt in roadways is. Then we'll have a brief intro regarding the load distribution on the flexible pavement. We already mentioned earlier that in flexible pavement, some people consider it a drawback. You know, you do have the stresses concentrated because of the flexibility. So whenever you have a poor soil, or if you have poor compaction for your subgrade, then there is a chance for bottom-up rotting, which again is to be controlled either by improving the geotechnical conditions through partial or full replacement added to this compaction. Some states now allow the use of geotextiles and use of geogrids to enhance the soil resistance or the subgrade resistance, or simply you can shift into rigid pavement, which acts like a beam and distribute the loads on a much larger area, which results in a smaller stress. After this, we will delve into different types of asphalt mixes. We have in the US still the lion's share out of the asphalt is the HMA, or hot mix asphalt. I guess it's going to be the same thing in Nigeria, right? Some states and some references, they call it ACHM, asphalt concrete hot mix, or HMA hot mix asphalt. Under hot mix asphalt, we do have dense graded. This is the standard mix. Then we have stone matrix asphalt, or SMA, which is basically like the open graded, but the aggregate is a little larger, talking about 30 to 35, about 30 millimeter, like slightly larger than 1 inch on the nominal maximum size, and with reduced amount of fine aggregate. So this is basically is used to enhance the capability of asphalt wearing surface to resist the top-down rotting. Then porous asphalt, which is not very common in the US because of some weaknesses, as we will talk about. After this, the warm mix asphalt, which is basically on the rise right now. It's not like a huge thing on the market, but it's getting higher and higher, especially in the northern states, because of the ability to do the mix at a temperature that is 50 degrees less than the hot mix. So there is a lot of advantages, whether saving on energy, better environmental compliance, health-wise, it's better for the labor because of the amount of smoke or vapors inhaled is much limited. Also because of its temperature, lower temperature, it can be used sometimes at night or into a much lower temperatures than the hot mix asphalt. And then finally, a temporary intro into the cold mix asphalt, which is really not used much. It's more into the very local use, into subdivisions or local highways, and it is basically used for a temporary purpose until, you know, the weather gets back to like spring season or fall season, away from the winter, and then they kind of peel it off and use warm or hot mix asphalt. So historically, asphalt started as a story more than 3,000 years ago. If you remember, there is that religious story about Prophet Moses when he was placed in a basket in the river Nile, right, to be protected or to not be persecuted. Then the Pharaoh daughter find him. You know, the basket, in order not to sink, it was painted by asphalt. So this is the very first mention for asphalt as an insulating material or a waterproofing material for Prophet Moses thousands of years ago. Then the Lebanese used it for ship making. It's basically, again, for insulation. So far this use hundreds or thousands of years ago was predominantly for waterproofing and to avoid sinking of baskets or ships. Then the Egyptians used the asphalt so that it can be as a rock binding agency to prevent the scour when the flood comes from Ethiopia or Lake Victoria or Uganda up north. So basically, it was also used as a binding agent and not the main purpose as for what we see today. So basically, this is the religious manuscript, a basket covered with tar on the River Nile a few thousand years ago, carrying Prophet Moses. That is the first mention the human history know for sure about it, you know, that it did exist. Then here in Babylon, and you see the ancient Greeks as well started to use the asphalt, which came from the word asphaltus, means secure, and basically that was used either water tanks or insulation or for ship building. Then in the end of the 16th century, the Europeans started to use asphalt after they founded the large world deposits of asphalt. So basically that was in Trinidad, close to Venezuela and, you know, Latin America. And again, that was more or less used for security and insulations of ships. Early 1800s or the 19th century, 900 miles of roads, that was the first mention for asphalt in the roadway construction. It came out of Scotland, and basically they used to paint or bind together smaller broken stones. Basically that is what started the road or paved the road into using asphalt in what we call the hot mix asphalts of today. Basically the initial use was to bond the broken stones together and kind of oppress the dust, so whenever, you know, the horse carts go through, you don't see a lot of dust evolving. So this is basically the initial attempt to use asphalt in the roadway construction back on the 1800s or the early 19th century. Late 19th century, it came through Belgian chemists, where they paved Pennsylvania Avenue in Washington, D.C. And anybody knows what Pennsylvania Avenue is in Washington? That's basically the address of the White House. So that's where Mr. Trump is right now. If any of you visit Washington, D.C. and stand in front of the White House, he is on Pennsylvania Avenue. They call it the Pennsylvania Avenue. So this is, so this is the first known roadway or known asphalt application in the United States in 1870 in Washington, D.C., Washington District of Columbia, the capital, right across from the White House. Early 1900, refined petroleum came, and asphalt construction or asphalt extraction as a natural asphalt, you know, was getting in there, and we started to produce what we call the traditional asphalt concrete to be laid by, you know, what we see asphalt pavers right now. Then with the 1942 and the World War II, you know, aircrafts had to use asphalt, and it was also used in the runways on the aviation business. So that was another introduction of the asphalt into the infrastructure, which is basically into the aviation industry. The big jump, it was by 1956. I think that was in Eisenhower's time. I was not alive in that. Any old guys here, 80 years old or more? So do you remember who was the president? I think it was Eisenhower in the 1956. They came up with the Highway Act. Now the word act is very common in the United States, where you want to do some national move toward one thing. They do what we call the act. The act has to come by agreement between the Congress and the United States President, and usually it entitles or allows the government, the federal government, to use several billions of dollars to do something. whether, act to construct network of bridges, network of highways, shift the country into a specific type of data, or health act toward using a special type of chemicals in the health industry or pharma industry. So the Highway Act came in 1956, which basically called for the standardization of the US lanes. Like if you study the highway system in the US, as I said earlier today, from the east to west, or the Atlantic to the Pacific, it is 5,000 miles. Every road crossing has a 5,000 mile length. We call it the I, the interstate. Could be going east-west or north-south between Canada and Mexico. If it has an even number, that has to be east-west. If it's an odd number, it has to be north-south. I'm not sure if this piece of information is there, but like if you get lost and you're driving on the highway in America, if it has an even number, it means you're going in the direction from east to west or west to east. If it is odd number, then it's going north-south. So think about the construction of several thousand miles of interstates. That required a lot of standardization to be done for the world of asphalt, or the business of asphalt. And that's where most of the standards were developed in the United States, including even the geometrical standards, like the width of the lane. It is 12 feet in interstates. It can be dropped to 11 feet into arterials. It can be 10 into collectors. And some people are calling even for 9 feet in the local, in residential areas. There are locals, collectors, arterials, and freeways. So freeways, 12 feet, that is based on the Highway Act. Then comes the 1970, that's where the asphalt started to really come into play with politics, when the Egyptian-Israeli war happened, liberation of Sinai. So the Arabs, to force the US to back off, they had to cut the oil supplies from the West. So the price of oil went way high, and that made the asphalt be very expensive. And at this point, all the studies shifted into trying to find ways to make economic decisions or use recycling with asphalt, because depending on a product that could skyrocket based on a political decision is not in the favor of any nation. In 1986, the National Center for Asphalt Technology at the Auburn University in Alabama in the South, they started providing what is like a push for the federal research. It's a new research center that kind of control the ideas for research over the 50 states. So it's kind of serving as an arm for the Federal Highway Administration. Then in 2002, the EPA, Environmental Protection Agency, announced that the asphalt plants are not on the industries considered as major source of hazardous material. The EPA in the US, they have the authority to give penalties, to impose taxes, to do whatever they want, of course, after consultation, with specific political parties. But EPA right now, they are making a major push against the cement manufacturing. That's why, America, I would say, I remember growing up in Egypt mid to late 70s and early 80s, when my dad was working in the Ministry of Housing. Egypt used to import a lot of its cement. Right now, there is a lot of cement in the United States that is Egyptian-made. In part because of political decision by the Egyptian government, also in part because of the US and some of the Western countries using the push by EPA and similar organizations in the Western Europe. They decided that cement has to be expelled as a manufacturing capacity outside their countries to protect their environment. Now this is not the case with asphalt, because of precautions that made the asphalt industry considered compliant with what EPA is requiring for the American society. Then today, basically everyone knows what asphalt is. Any contractor, small or large, knows on the 50 states. So the question is, what kind of sustainability or what kind of research can we do, whether to make it more compliant with environmental, aspects that's becoming more stringent with time, or make it more economic, or enhance its durability, long-term performance, or come up with new types of asphalts which can, fit with different environmental challenges as what we have right now in the United States. So this is basically a brief abstract or a brief snapshot of the history of asphalt and how it started from a biblical or religious story thousands of years ago all the way until it became in the forefront of the materials that are used and presenting a big chunk of the GDP of the United States or the rest of the world. Now, having that said, why are we still insisting on flexible pavement? Think about ease of construction. One thing now with asphalt, especially with all the available types of machinery, it's very easy to construct asphalt. You can have very good ability to whether do quantity takeoff, do scheduling, do planning, etc., using asphalt, because it's an industry that is known in and out with very precise specifications for all the stakeholders, whether the owner, the project manager, the contractor, or even material supplier. Other thing, it's ease of maintenance, also the cost. And here, when I mention cost, I have to make a disclaimer statement. It's a 35% cheaper, but I'm talking now about the initial cost, because hard pavement people, if I mention this statement without the disclaimer in a conference, they will be running after me with a stick after the conference is over, because our product is more expensive at day one. However, if you think about 25 years old or 30 years old project, and you add on after you factor in the inflation, and you bring everything back to the net present value, for those of you who study life cycle cost and understand what I mean by net present value. So you will find, or that's the war that is happening right now, that asphalt is 35% cheaper, including initial cost. But concrete will end up being in the neighborhood of 5 to 10% cheaper if you include all the preservation and maintenance cost through the lifespan or the service life of the project. Environmental compliance, everyone knows what RAP now is, right? RAP, recycled asphalt pavement. In the US right now, there are two major terms that we have on the business of asphalt. It's RAP and RAS, RAP and RAS. RAP is the recycled asphalt pavement that we know, and RAS is the recycled asphalt shingles. In the US, especially in residential construction, wooden construction is used big time. So they have asphalt shingles on top of the roof, right? You see those shingles. So 20, 30 years ago, they usually tell you 15 years is a good lifespan for the shingles. After this, its ability to do insulation will go down, so you have to change. And usually you pay a monthly premium for insurance companies, so when the time comes and you want to rebuild or redo the insulation on the roof, basically they can contribute 80-90% of the cost through the insurance. Nowadays the story is being shifted. Some companies are after you to do the maintenance. Why? Because right now they send the crews. Normally construction workers in the US, a lot of them are from the Latin part of the America, like South America. They go above your roof, and then they do have metal pieces like the ones you use in farming, basically, and they peel off your roof, throw it down, and then they ship it to batch plants, asphalt plants. So normally or standardly, we have 5.5% of our hot mix asphalt is a binder content. You wouldn't be surprised if a couple points or a couple percent are an outcome of this RAS or the RAP, like close to 33%. So this is because of recycling. So asphalt is much more recyclable compared to concrete. You use recycled asphalt in the binder, but if you use concrete in recycling, you'd basically crush it and use it as aggregate for the new concrete. You still have to come up with your cement. So recycling of asphalt is more beneficial. Other thing which is now coming into play, especially with the EPA, the carbon footprint of the asphalt, even with all the heat during, construction, is much less than cement. Anyone here knows the carbon footprint of cement, how much it would be? Okay, if you Google that, it will be almost 1-to-1. That means a 1 kilogram of cement evolves 1 kilogram of carbon dioxide. A 1 ton of cement evolves a 1 ton of carbon dioxide. This is huge. I was reading an interesting study that the amount of concrete, or basically the cement used in the concrete, that is used only in the Empire State, in New York, is equivalent to the carbon dioxide that evolved from, now I don't remember how many trips, but they compared it to round trips between JFK, the John Kennedy Airport, and Heathrow Airport, back and forth by a Dreamliner, the Boeing 787. So they calculated the emissions by 787 in one trip from New York to London, JFK to Heathrow, and it was a small fraction of the amount of cement that evolved, the amount of the carbon dioxide that evolved in manufacturing the cement that was used to mix the concrete that is used only in one building, which is the Empire State Building in Manhattan in New York City. And there was many trips. I mean, I would say like a few hundred trips of a Dreamliner. Round trip trips is only equivalent to one building. So think about the footprint of cement and the footprint of if you do rigid pavement. Now, resilience, you may disagree with me, and I would understand this. Same when I teach this or I do this seminar in the Arab countries, in the Gulf or in Egypt. In America, they consider asphalt is more, I'd say, resilient, because a huge part of the destruction that happens is because of the frost heave. Think about frost heave, as I mentioned, the water freezes underground, so it pushes up. Now the asphalt has high flexibility. It's called flexible pavement. So the amount of cracks or the minor cracks that are developed will be smaller compared to when you have a rigid pavement. Now that would be not the case in Nigeria, not the case in Egypt. Also, think about rutting. That's what the rigid pavement manufacturers reply. I'm here strictly talking about frost heave, which results into uneven, push up onto the pavement. The flexibility of the asphalt give it or makes it a better candidate. Other thing is de-icing salts. In the US, a lot of places on the Western world, they use salt on the highways. You know that, right? Because of, it's freezing temperature oppression. That's what they call it. Normally freezing temperature is 32 degrees Fahrenheit, or 0 Celsius, which is a very easy temperature to be attained in lots of the states in the United States, with the exception of few states like Texas or Florida in the south or New Mexico. The rest of the US, including where I live in North Carolina, we see that temperature quite often, for 3-4 months. So what the de-icing salts, sodium chlorides and calcium chlorides does is they push the freezing temperature down to -15 and -20. So basically, if you have rain, or if you have any sort of water and on the highway, and the temperature is -5 or -7 or -10, you will not see ice. So the use of these salts, it's okay to use it with flexible pavement. But if you use it with rigid pavement, especially if you use rebars for temperature or shrinkage compensation rebars, then you get a big problem with this thing. Also in asphalt, the need to construction joint is not there as in rigid because of, again, flexibility and ability to sustain the lateral movement. Now coming to load distribution, as the engineer here said earlier today, this is one of the major, I would say, advantages when it comes to rigid pavement. Why? Because the pavement, whether it is 8-inch or even more, it acts like a rigid beam. So the way it distributes the stress, as you see in the top left, it's much larger area. And when you divide the force on a larger area, that means lower stress. So the subgrade here is not affected or is minimally affected. So if your subgrade is not really well graded, or you didn't do partial or full replacement, or you didn't do a huge compaction to your soil, still you can get away if you have a rigid pavement. But if you have flexible pavement, you can see that the stress is localized or concentrated into a much smaller area. And that makes the stress extend through the base, subbase, and quite deep into the subgrade. So if your subgrade here is not well compacted, then you can easily end up with a problem. Now in general, the United States, the specs, the ASHTO specs, it calls for 100% of the compaction for the soil or the subgrade under the pavement layers and 95% under the sidewalks. So I'm not sure, did you have similar specs here in Nigeria where you have a minimum percentage? Like, what do you require the contractors to do when it comes to the compaction? Is it 100%, 98, 95? 100? Okay. So it's always safer to require higher compaction. You can never guarantee what's going to happen down the road, especially with all the increase in the number of vehicles and the loading per vehicle. Now coming to the types of asphalt mixes, I guess it's pretty standard. The only differences is how to proportion our mixes, whether we are using Veeam or using Marshall or using Superpave, or now after Superpave we implement the balanced mix design. These are all developments when it comes to proportioning our asphalt mix or fabricating the samples to be tested. In the Superpave, we will talk about how you form your sample using the gyratory compactor and what type of testing has to be done so that you kind of simulate the real life loading that happens from the tires and tire pressure. But when it comes to types of asphalt, it's pretty standard all over the globe, with a little bit of unique designs for what we call the stone matrix asphalt in the US, and I think Canadians are using the same because of the amount of trade going back and forth between the US. There is a NAFTA, which is, I think it's North America, something trade agreement, federal trade agreement or something like that, where you have thousands of truckers going back and forth between the US and Canada with thousands or hundreds of thousands of tons of cargo. So in order to fight this, they had to develop the stone matrix asphalt, or the SMA, which is a type of the hot mix asphalt, as we see, with different type of gradation for the coarse aggregate. So here, these are the temperatures used for hot and warm mix asphalt. So 150 Celsius and above, or 100 to 150. Normally, for hot mix, we're talking about 160, maybe 170 for hot mix asphalt, and about 110 or 115 Celsius for the warm mix. Is it about the same here in Nigeria, or Do you do any differences? 160 and 110? Yeah. But how often do you use warm mix asphalts? Not. But why? I mean, maybe I can understand this in Nigeria because you don't have the. Do you have any cold weather anywhere here in the country? Very limited, right? Yeah. Now, when I teach this course in Bahrain and Qatar and in Dubai, they know what warm mix is, but they predominantly use the hot mix because basically there is no much need for reducing the temperature of production. And hot mix will be cheaper because in order to compensate for the difference in temperature you have to use emulsions and additions to make the asphalt as flexible under lower temperature as it is for the high temperature or hot mix asphalt. So now for HMA, we have three types: the dense graded mixes, the stone matrix, asphalt SMA, and the porous asphalt. So I guess here probably dense graded will be the most, right? And what type of coarse aggregate do you use, like up to 25 millimeter? 19 and down. Okay, so but probably you'd end up with a lot of rotting this way. You know, yeah, because right now even with dense graded we push more than 19, and with stone matrix we push up to 30 millimeter, or like 1.25 inches for the coarse aggregate, so that, you know, it's better for fighting the ruts. So dense graded, again, there are few factors which we have to think about. One is the aggregate shape. The second one is the workability of the mix. The third one is the binder content. The fourth one is the aggregate size. Now, the aggregate size, as I mentioned, it is very important because it can assist, you know, the coarser the aggregate, the better its contribution to fighting the top-down rutting through bearing between aggregate particles. The binder content, in the US I noticed we're slightly higher than most of the Gulf. Like in the Gulf they use 4.5, maximum 5. In the US 5 is about the minimum. Sometimes they go to 5.5 or even 6. There is about a 1% extra on the asphalt. Now there are pros and cons. You know, if you add more asphalt, maybe it's good for raveling because you have enough asphalt surrounding your aggregates. Maybe it could be good in fighting cracking. You know, the more you encase your coarse aggregate, the lesser the impact of the temperature on expansion and contraction, so the better it will be in fighting the cracks. However, it's not good for ruts. So more asphalt means more money spent and lesser resistance for rutting. Workability, it's predominantly related to the temperature of the mix. And if you drop the temperature up to 50 degrees to develop the warm mix asphalt, then pretty much you can compensate to this by adding emulsions, specific types of emulsions, which would result into same workability under minimized temperature. Now, aggregate shape, we know there are different types of aggregate shapes. For coarse aggregate, I mean, there is rounded, there is angular, subangular, there is flaky. So pretty much we can use any type, but you have to watch for the percentage, except for the flaky ones, because these would minimize the flowing ability because of the amount of bearing between the aggregate particles. We will talk about that in details when we talk about quality control. Now, shapes and types, we all have done this in our college, right? Sieve analysis. Do you remember that, or any good memories? I mean, we've done sieve analysis in different classes, actually. We did that in concrete design. We've done that in asphalt. We've done that in geotechnical or soil mechanics. And I always mention this because, you know, I do teach concrete and I do teach soils, and I do teach asphalt, everything relevant to materials. And basically, when I teach concrete, when I talk about the aggregate, do you remember what sieve separates between coarse and fine? You know, sieves, you either classify the sieve by the size, like when you say 1 inch, it means the opening, the net opening is 1 inch, or 25.4 millimeter. Or you can make a hashtag and a number, like number 10. That means what? 10 opening in 1 linear inch. Number 20, 20 opening in 1 linear inch. Number 100, 100 opening per linear inch. So if you talk about that number thing, the higher the number, the smaller the opening, because it tells you how many openings in 1 inch. But when you talk about dimension, the higher the number, the bigger the opening. Okay? So back to the initial question. What is the safe size if you are in a materials class that separates between coarse and fine aggregate? Like, let's say you work in a concrete batch plant, or you are in the business of rigid pavement, and you're talking to the technician, or your boss is talking to you, and he mentioned the word, how much coarse aggregate do we have? What does he mean by coarse aggregate? It is aggregate retained on sieve number 4.75 millimeter. That's the dimension. Or number 4 in the number. So sieve number 4, which means 4 opening per linear inch, or 4.75 millimeter. Now 4.75 by 4 is not 25.4, because there is width for, because I get that question a lot from everybody, is like, if 25.4 millimeter is 1 inch, then how could 4 openings makes 4.75? Because there is a width for the rope itself. So if you have 4 opening in a linear inch, or the dimension, the net dimension of the opening is 4.75 millimeter, and your aggregate is retained on top of it, that means it's coarse aggregate. If it passes through, that means it's fine aggregate. Now that's if you are working in a batch plant of, or if you are talking about rigid pavement. Now let's take off this hat and wear the hat of asphalt plant. Or before that, geotechnical, if you are doing a geotechnical report for the highway department, what aggregate is, or what type of particles in the soil that are geotechnically considered fine, and what particles are considered coarse? What is the sieve? Is it still number 4? No, 4.75 plus coarse, that is for concrete or aggregate in the concrete business. But for geotechnical business, it's sieve number 200. So 200 opening per linear inch. It's much, much finer. It's a micro size. Why? Because in concrete, you have only limestone and sand. So one is coarse, one is fine. But in soils, you have the limestone, you have sand, you have silt and clay. Actually here, driving from the hotel with Engineer Isa, I can notice a lot of clay in Nigeria. So if you do sieve analysis, whether you have clay particles or sieve particles, that will pass from sieve number 200. So it's a microscopic compared to the fine, which is considered in concrete. Now when it comes to asphalt, it depends what we will talk about this, because some organizations in the US consider number 8, others consider number 10 to be the difference, or the one that distinguish between coarse and fine on the asphalt industry. So specs are not the same. And I always get like students roaring at me. It's like, you told us last semester that what's passing from number 4 is coarse. Now you're telling us it's still fine. Well, but last semester was a materials course. This is a soils course. So, so always remember which hat are you wearing, right? So other than that, you know, the strengths of the aggregate, the maximum size of the aggregate is another important factor. As I said, you know, 25 is used, 25 millimeter in a lot of the applications. We go up to even 30 millimeter if we are talking about stone matrix for you know, fighting with ruts. Now here is what I am talking about. So fine aggregate, mainly sand, it passes from sieve number 4, which means the dimension is 4.75 millimeter. And here I put why it is called number 4 because it's 4 opening per linear inch. Coarse aggregate, it's crushed granite or limestone, it is retained on number 4. Again, that is in a concrete setup. In asphalt, it will not be number 4, it will be number 8 or number 10. In soils, it will be number 200. Now, the particle size distribution or degradation, why do we consider this as something very important for HMA? What do you think the outcome is going to be if you ignored this? Let's say you use the same size aggregate. What's going to happen? What's that? What if you use all of them, like let's say use the same size? Exactly, exactly. So again, if you use the same size in a concrete, the strength will be jeopardized. Your 28-day compression strength will be jeopardized. If you use the same size in soils, you better off do partial or full replacement because compaction will not gonna get you any better. If the soil particles are about the same size, keep compacting the soil for 2 days. You're not gonna increase the density because there are no fine particles to be embedded between the coarse particles. Now, if you do that for asphalt, you'll have a lot of voids and then you will end up with a much lower in durability. Trust me, cracking will hunt you. You know, and if it is same size fine, rotting would also hunt you. So now this is again for aggregate classification, and here I'm talking about the most important standards we use in which is basically the ASTM. They highlight, sorry, the highlighted by ACI, American Concrete Institute. So this is for the you know, reinforced or concrete in general, concrete business. Now, in our asphalt, do you remember this phase diagram from soil mechanics or from asphalt or even ACI, American Concrete Institute mix design for concrete? They call this phase or block diagram. Now, all the mixed designs, whether you talk about a mixed design for concrete, how to proportion the constituents of concrete. What are the constituents of concrete? You have cement and water, that is the hydrated cement or the glue, and then you have got the filler, which is coarse aggregate and fine aggregate. Then you've got 7-8% of voids. Maybe you can have some admixtures, maybe you can have steel fibers, maybe you can have, but that's a fraction of a percent. But this phase diagram or block diagram for concrete business is cement, water, coarse aggregate, fine aggregate, and air voids. And you have to proportion this so that volumetrically they add to 1 unit volume. In the US, we call it a 1 cubic yard. Here in Nigeria, we'll call it a 1 cubic meter, right? This is how you claim victory when it comes to the design of a reinforced concrete mix. Same in soils. But in soils, what is the phase diagram made of? Anybody remember? Back to school. 20, 30, 40 years? Well, no, there are ladies here. 1 year ago, 2 years ago, 3 years ago. Because all ladies here are fresh grads, right? You graduated last year. How dare you say this? The first brave lady to claim that she's 15 years in graduation. I remember until my mom's died, she graduated last year. So yeah, she had a rule. A lady will never go past 31 years old. That's my mother rule. She goes up to 31 and then she levels. I mean, thank God it doesn't go back like a parabola, right? But yeah, but if, again, talking about concrete, you're talking about cement, water, sand, gravel, and voids. Soils, you're talking about solids, which could be gravel, sand, silt, and clay lumped together, then water, and then air, right? The addition of the three, the solids, that's what your soil is made of, right? A mix of gravel, sand, silt, and clay, the 4 main constituents. There could be some organic matter, but then plus water if you're under the underground water table, plus some air voids. Now, when it comes to pavement, we do the same, but think about this. You have the aggregates. I'm talking here about the wearing surface, not the subbase or the base. The subbase or the base, you treat it like soils, more or less. But here, you have aggregates, then you have asphalt, which is 4.5, 5%, and then you have air. But then, remember, on the asphalt, there is something unique, because the binder is different than the hydrated cement. The hydrated cement, it goes around your aggregates, right? It never penetrates the aggregate. Here, your asphalt, if you use, let's say, 5% free binder content or asphalt concrete, and you add it to your aggregates, do you think after you mix it, you'll have still 5%? Some of it will enter because, yes, it will be absorbed. This is a difference in color between aggregate and asphalt. You see a strip with absorbed asphalt. Do you see this? This is extremely important, which is, if not calculated, you will end up with a much lesser binder content in your mix than what you think you already have. And basically, there is a lot of testing. There is a kerosene test. I'm not sure if you do the kerosene test for your aggregate to quantify how much kerosene the aggregate would absorb, and this is an indication. It's indicative of how much binder your asphalt would absorb. If you don't do this correction before doing the mix design, you'll have on paper or on your mind a mix that is not there in real life. And think about the impact. What's going to happen here? Lots of cracking. Because you think you have 5% or you need 5%, you drop down. It's going to impact hard every property. However, the cracking resistance is the #1 property to be impacted if you do not account for this strip of the asphalt that is absorbed. It's no longer free asphalt. It's non-existent. You treat it, disappears. It is like, if somebody has done lightweight concrete construction here, you have expanded shales or clays. I've done a few projects for bridge decks using lightweight concrete because you want to reduce the dead weight of the bridge deck. So if you use lightweight, it has a lot of voids in it. If you mix it straight in the concrete, you will never have a concrete mix. It will be a super dry mix because it can absorb up to 30-35% water. So if you add, let's say the ratio is about 1 to 2, like water cement ratio is close to 1/2. So let's say in a cubic yard or cubic meter, you have 350 kilograms of cement, then you use about 160 kilograms of water, right? Now, if the absorption capacity is 35%, right? What's the weight? The weight of the aggregate is several hundred kilograms. It represents like 75% of the weight of the mix. So it will literally absorb all the water. Then the cement will be a dry powder. You will not end up with a concrete. So before you do this, you have to submerge and let it stay overnight in barrels full of water, the aggregate. Then you flip the barrel, you make some sort of filtering for the water. Sometimes we use burlap or cloth that we use for curing of concrete. You let it dry, then the aggregate now is what we call SSD, saturated surface dry, meaning from the inside is saturated, from the surface it is dry. Then it's now optimized aggregate to be used for the concrete manufacturing. You do the same thing here with asphalt. You have to quantify through the kerosene test what is the portion of the asphalt that will be absorbed by the aggregate. And then let's say it's going to be 0.75%. Then if you need 5%, do 5.75. This 0.75 is gone. You're left with the 5% which you were targeting from the very beginning. Otherwise, cracking would happen in no time. So this is an extremely important parameter when it comes to the aggregate gradation and the ability of the aggregate to absorb water from, binder from the mix. Now, manufacturing temperature is important. As I said, it affects the workability. So think about the numbers. I'm putting the degrees in Celsius between bracket, that 270 to 325 is Fahrenheit. Do you know the Fahrenheit? How do you convert to Celsius? You subtract 32 and you multiply by 5/9. Some people divide on 2. Like instead of 5/9 is like divided close to. But the exact way, whatever you have in Fahrenheit, deduct 32, and the outcome multiplied by 5 divided on 9. So the temperature that is 0 is 32. When you say 32, that is 0. So in America, 32 degrees, everybody is in jackets. Now, in summer, when you say it's 100 degrees, that's when they consider it hot. 104 is 40 degrees. So usually, it's about an unwritten rule in the whole United States. Once the temperature hits 100, which is about 38, 38.5, you get what we call a heat advisory. So we had that last week when I was in America. We had that heat advisory, which means if your air conditioning at work or in the car is not properly working, stay at home. And I literally got that from my boss, the department chair, because they figured out they have an issue with air conditioning. They said no faculty should come, because if somebody got ill, you can sue, you can have a court case. Well, you impacted my health. So temperature 270 to 325. I mean, we say 150 to 160 degrees. That's for the hot mix asphalt. And of course, that depends from where the manufacturing facility to the final project destination is. Pretty standard in America, we never allow the mix to drop more than 10 degrees below the temperature of mixing upon placement. So you have to make sure that the distance is not too huge. Huh? Well, we specify the distance that result in a drop no more than, because it depends on how colder the temperature, like in colder weather, you have to be closer than when it is hot. So the distance is not specified, but the drop of temperature is specified. So if the distance will make you violate this, then it's not a good distance. You see that? By the way, we have the same story with RCC, roller compacted concrete, but it's not the temperature, it's the workability. Why? Well, temperature comes to play. In roller compacted concrete, as I mentioned earlier, it has to have 0 slump. So when you do the cone test, 0. So that means the concrete is very dry. Let's put it this way. So if you have your truck mixer filled more than 1/3 to 1/2, you know, the rotation is not going to be efficient in maintaining the workability. So it hardens. It hardens inside the truck. So that's one of the major concerns of the contractors who does the work in RCC. When they do the pricing for the project, that's one of the reasons the cost goes up. They tell you to transfer the product from the plant to the roadway, we use double or sometimes triple the number of trucks, because it has to be almost empty, like 30% full. Because if you put it at high capacity to cut down the expenses, it will harden inside the truck. So this problem is always there in the highway industry pavement, whether you use RC, roller compacted concrete, or you use flexible pavement. Again, there is no stringent rule other than maintain the workability for RCC, not maintain the workability, I mean, don't make it harden or initially set. And for hot mix asphalt, don't let the temperature drop more than 10 degrees. Uh-huh. that will be a huge problem, because how can you spread it? How can you compact it? That is what's going to happen. Do you see what's going on? So basically, that is what's going to happen to your mix, your asphalt. It's a pie crust, because you will never be able to do a good compaction if the temperature drops. So you will end up, the pie crust, it's going to be harder at the surface, at the bottom surface where you meet with the aggregate, and then it will be fluffy on the top. And that is, if you remember when I talked in the presentation right before, the second presentation, right before lunch, poor compaction would result into ruts. So this is a huge outcome if the temperature was not monitored, if you allow a lot of, greater than 10 degrees. Now, one thing you can do, and that's what we are tremendously using in the US, is shift to warm mix asphalt. Like, state of New Jersey, state of New York, I know for a fact, I have colleagues working that I talk to quite often in New York Department of Transportation. New York is like the cash capital. They have Broadway, they have the stock market. So, and they have 4 or 5 months of cold weather. So they cannot have the asphalt, especially in Manhattan and in the Wall Street, and so in poor shape until the summer comes to fix. They need to fix it even in the middle of the winter, in the middle of the night, and think also of traffic. It's huge. So blocking a road will cost thousands and hundreds of thousands of dollars. So they end up doing the business at night in the winter. So that's why they shift to warm mix. They go to temperature down to almost 100 degrees. That's about 50 or 60 degrees less. Now, this one, even it drops 10 or even more than 10, it still is not gonna give you the same hard time as, or the pie crust thing, as the hot mix asphalt. Even like in JFK, John Kennedy, in O'Hare, Chicago, I'm saying the most important airports in the US, if they want to fix the runways, they want it fast, they want to do it in the middle of the night, in the middle of the winter, and Chicago could be 20 below zero. Warm mix asphalt is being used. So because of its ability to achieve good compaction even if it cools during transportation. So this could be an option if you do project in remote locations in Nigeria where you can't have an asphalt plant close by, or the distance is huge to the point that you'll have a major drop in temperature. Instead of doing the pie crust thing and end up with tremendous rotting, probably pay the extra penny. I mean, usually warm mix is about 10% higher because of you're adding emulsions to compensate for that drop in temperature, but it's worth it. So here, these are temperatures, again, air, concrete, and asphalt. Okay, so sorry? You mean the 150, 140? Uh-huh. For construction?
Is it for production or for laying?
Well, if you produce on 150,
Yes.
you can drop to 140.
Sure.
That's fine. Or 140, you can drop to 130. So this is, it could be either or. Again, the difference shouldn't be more than.
Is it independent? Is it dependent to the air temperature?
Here, yes.
Okay.
I'm not sure if I get your question. So if the air temperature, let's say, is
If the air
97,
temperature, let's say, is 91 degrees, what is the expected laying temperature of the
okay,
asphalt?
I got that. If the temperature is close to 100, let's say 97,
Yes.
then it's better to do 150 degrees. So
Right.
this way you don't have a huge difference, or in other words, you have a chance that by the time you transfer from the plant to the site, it's not going to drop much. But if it is 150 and you do at 85, remember temperature, you know, it's heat radiation, right?
Yeah.
So if you have very cold temperature and you have very high heat, you'll have a huge loss in the temperature. This is what the slide is trying to tell. So basically it's giving you a guidance on, you know, what kind of temperature you do the mix at,
Yes.
right?
No, it's on the because it's different with our own. I think our own is we produce at 143, are we? 143. So by the time we do our haulage distance to the site, it will now lay at 130, 120, 130.
Yeah, 143 to 130, it's very
Yes.
close. I mean,
So it's because of our temperate region. Eh? You do understand it, but no problem. I got the point that you're trying to raise.
yeah,
Thank you.
yeah. Yeah, just the point again is the colder the air temperature, you better be careful with the mixing temperature, because the bigger the gap between the two, the faster the chance you will lose. That's why, you know, when you get, as I said, in New York, in New Jersey, you tend to use warm mix, which is already much cooler, so that the loss in temperature is minimized. It's gonna make sense? Excellent. So yeah, this is a very important parameter when it comes to work with asphalt, because of, again, you don't want to end up with that pie crust thing. You don't want to end up with a very low durability, predominantly rotting, that you know, could exist if you are having, you know, you end up with the pie crust type of concrete mix, asphalt mix, or asphalt compacted mix. Now, the workability, or how would you compensate for the drop in temperature? That is basically where the emulsions come in. You know, everyone knows what emulsions are? It's like when you mix the binder, you know, you add the binder to the liquid, to the water per se. Instead of having a localized precipitation, you add emulsions so that it can be an even solution, right? So this type of emulsion, you know, again, if the temperature is reduced and up to 50, sometimes 60 degrees, from 150 to 100 or 90 for warm mix, that would affect the workability. So in order to make it workable, it is like, you know, when you produce concrete under low water content, sometimes you drop the water to maintain the strength. You know, low water means higher strength. But then how about workability? You need workable. So you add super plasticizer, which makes the mix flowable without water. So this is basically kind of the same thing. It makes high, you know, workability without adding too much temperature or too much heat. So emulsions, that is a huge market. And you know, chemists do, like, I mean, personally, I deal with whatever I need in my lab. I don't know all the characteristics, but I got from the specs. These are, you know, the different types: anionic, cationic, non-ionic. Again, I basically look at what I need and I use. I don't really go, I'm not a chemist, so I do not go in deep details on the type of emulsions. I know I need to produce this type, I need to overcome. If the boss is up, everybody has to be up. Yeah, you remind when I fly from the US, I always go to the back of the airplane to the flight attendant. You want tea? No. You want to go to the restroom? No. What do you want? I want to do
All right, good luck.
Everybody's refreshed? Is everybody refreshed or everybody's sleeping? Oh, no sleep. Good. Okay. So come to a very important mix, which is called the stone matrix. This is what you see. The left-hand side is a section on a stone matrix asphalt. The right-hand side is a conventional hot mix asphalt. Again, don't mix things together. Stone matrix is a hot mix asphalt. Same temperature, same block or phase diagram, binder, aggregates, absorbed binder, voids, everything is the same. The main difference between the two is you are using more coarse aggregate on the left one. And why is that? Because coarse aggregate, they do have the bearing on top of each other. So when the vehicle or the tire or any type of pressure is applied on a wearing surface, when the compression happens, if you don't have that coarse aggregate, you know, the wearing surface itself is flexible. You would start seeing slight rutting that would expand, and that is a top-down rutting. Has nothing to do with the bottom-up rutting, right? So having the stone matrix mix, which is a higher percentage of coarse aggregate, and usually this coarse aggregate is 30 millimeter, you end up with huge bearing force, which is great in fighting rutting. They use this a lot, like in, let's say in lots where you have like workshop or a lot of cargo stored, some highways where you expect a lot of vehicles, you know, like in trade or commercial corridors, stone matrix is being used. Now, overdoing it, there has to be, you have to draw the line at which you stop. Because if you overdo that, rutting is going to be happy with you. But trust me, your asphalt will crack in no time. And again, the reason is, you know, the coarser the aggregate, the higher the tendency it will be, or the more prone it will be to expansion and contraction with thermal or temperature changes. So in such aggregate type, if you overdo it, it will be good in rutting, but then expansion and contraction will end in cracking. By the way, that is a selling point for roller compacted concrete. As we know, in concrete, regular Portland cement concrete, even for rigid pavement, you use coarse aggregate and fine aggregate. Now in roller compacted concrete, you extremely, you know, increase this, the amount of the fine aggregate, and you make a cap on the size of the coarse aggregate. So the coarse aggregate is smaller in size, lower in percentage. That is for roller compacted concrete, in order to be able to roll it by the asphalt paver. So because of this, you end up with a mix that really doesn't have the same expansion and contraction like traditional rigid pavement. So the sellers of the roller compacted concrete, they tell you, yes, it might cost you more, it might ask for more trucks to transfer, but you might end up eliminating all the steel bars which you use in resisting the temperature change. So a lot of the projects done with roller compacted concrete, you have, it's pure concrete, plain concrete, no reinforcement. You don't need shrinkage rebars. So that drops the price. It kinds of offset a little bit the cost you incur during your transportation. So stone matrix is a gap graded mix. You know, in the Gulf states like Dubai, Abu Dhabi, in Saudi Arabia, when I mention the word stone matrix, everybody's silent. They call it gap graded. So basically, SMA is very good in rut resistance because of, again, stone on stone contact. However, I have to mention here, it's a little, not a little, it's 20 to 25% more expensive because of the stringent specs for you know, the aggregates. Also because of the higher voids, you end up usually adding slightly to the binder content to fill these voids. You don't want everything to be full of air, right? So that adds to the cost of the mix. But it is offset when you do the life cycle cost because of, you know, the longer lifespan and the lower need to maintenance. So here, that is what stone matrix, hot mix asphalt. Again, stone matrix is a hot mix asphalt. The main difference is the size and the proportion of the coarse aggregate. So it is used for surface course on high volume interstates or highways where there is a lot of cargo transfer to fight rutting. Okay. So stone matrix asphalt, again, as I said, gap graded. Manufacturers, they soak, you know, the mineral filler all, you know, combined into final gradation. So that has to be considered. And then the asphalt binder, you could use a modifier, again, because of the type of workability is gonna be a function of the voids. Normally a coarser aggregate, and remember this even when you do, even in regular concrete mix design, if you add a lot of sand, you need to add a lot of water because of, you know, the surface area would increase with a fine aggregate. Otherwise you would have a very highly workable concrete mix. Same thing here. So the workability has to be played in as a factor when you proportion your binder and when you think of adding emulsions to the mix. The last one is the porous asphalt. Oh, I made a problem. It's a porous, not SMA. Well, sometimes it's called SMA. I've read that a couple times, but it shouldn't be like this. They consider it SMA because in porous asphalt here, it is like SMA. However, it's not only coarse, but it's coarse and very poorly graded. It has basically one size. Why? To ensure the existence of huge amount of voids. And this is because of, you know, the permeability. This is under rain, it's in parking lots. I'm not a proponent of this. I have seen this test, I have mixed, I have witnessed that. You can see literally a very good outcome. However, one thing you keep in mind with permeable asphalt, because of the coarse binder, especially in parking lots, you use that in parking lots for like here in ShopRite per se, or Walmart in the US, where you have tons of cars. It's very dangerous because the surface is rough. Now, especially with Gen Z, there is a lot of skateboarding people, or if you have people working with like a cane, older people, they trip. And you know, some states in the US, they said no more use of this because of the amount of court cases that elder people, you know, take them to the court, or even younger ones, because the skateboard got stumbled because of the roughness, and you know, they end up failing. So this is basically a section of how the porous, do you use porous asphalt here in Nigeria? Very rarely. Yeah, same here, same in the US. As I said, a lot of the states already banned using the porous asphalt. So that thing concludes. Remember, we have talked about the history, how asphalt started, and then the different types when it comes to the gradation and when it comes to the temperature of the asphalt. Now, when it comes to the design theory itself, right now everybody shifted design-wise to the super pave, and then even after the super pave, we're heading into the balanced mix design. Now, I'm not sure, Engineer Isa, do you want to keep continuing, or I'm not sure about the timing. Should I keep going, or should we keep this for early tomorrow? I mean, it's up to you guys. Is it what? I can't hear.
Okay, we can take questions and answers now. Continuing tomorrow. We are still here tomorrow.
Oh yeah, I'm here tomorrow. The reason I'm slowing down here is the colleague engineer, what's his name? What's the other guy? I forgot, from Ghana.
Okay.
He sent me an email and he said he wanted to talk about Super Pave.
Okay.
So, I mean, he just sent it after. Okay, so the bosses here are saying it is time for Q&A. Anybody is awake? That's my first Q. Any answer now? No answer. Everybody's sleeping. So questions. Remember, we talked about general infrastructures. We talked about special transportation infrastructures. Right? Yes, sir.
Because I must say I'm exceedingly exhilarated for today's lecture because it reminds me of some of the international lectures I used to have in those days. Like when you mentioned Pennsylvania, that's the first place I observed cold in place asphalt recycling. Then when you mentioned Washington, D.C., that was when I had my percent within limit specification lecture in Federal Highway Administration.
Yes.
Then you mentioned Auburn University. That's where the first training I had in SuperPave in NCAT, National Center for Asphalt Technology. But what I've learned from you today is the phase diagram of mixed design that absorbs asphalt. Maybe I must have been hearing it during attending. I've also been attending a lot of seminars and conferences in the world of asphalt and asphalt reclaiming association in US. I've not noticed that absorbed asphalt.
Okay.
I do the design. I don't always consider it.
No. It has to be there.
Yeah.
I mean, whether they mention it or they do not mention it.
No.
Remember, this is a volumetric mixed design. So, meaning volumetric is you try to find the components that add up to 1 unit volume, right? Whether the unit volume is cubic meter or cubic yard. The unit volume of the ingredients. Now, the ingredients in asphalt, the major difference that it does compared to any other ingredients, whether we talk about soils or we talk about concrete, is that the intermingling between the binder and your aggregates. Like, let's take the analogy, compare asphalt or flexible pavement design and rigid pavement design. And rigid pavement design, voids is here, flexible, you have voids. Asphalt, your aggregates, right? In both. Now the binding agent in concrete is what? Hydrated cement. You see it? Cement and water. Will the water and the cement paste go inside the aggregate? It will never go. It will go between the aggregate particles, but it's not gonna penetrate. Like if you get a piece of rock or a limestone or a crushed granite and you try to analyze it or break it, you will never find cement or water and cement inside it, unless you talk about special case like very lightweight, like expanded shales or expanded clays. Now, when it comes to asphalt, the binder would infiltrate. That is the only difference. So hydrated cement will never infiltrate the aggregates, but the binder or asphalt cement would infiltrate. Is it a huge percent? No, we talk about 0.5%. But if you didn't think about this 0.5%, I mean, think about your asphalt. It's not like 20% like in cement and water. It's only 5%. So losing 0.5%, it's losing 10% of the binder.
Okay. I also learned about the one-to-one carbon footprint of cement and carbon. But in asphalt, I know EPA, European Pavement Association, says it's about 27 to 45 kilogram per ton of asphalt produced. But from my research in Nigeria here, I have discovered it's go up to about 75 kilogram of carbon dioxide per ton of asphalt. And one other thing you said, which I wanted to, in a lighter mood, you said the coal mixed asphalt is for temporary fix. Yeah. I have patent right on it. My cold asphalt are produced. The additive, the proprietary concentrate are used. It could be used for any highway. It could be used for asphalt overlay. It to be used for long haulage.
But how much cost it will be? Because you're adding chemicals. That's the word you mentioned.
You have arrested me.
All right. Please. Question. Just raise your hand. Okay. Please put your hands together for yourself. This last, they understood everything you thought.
Okay. All good? No more questions, no nothing?
Yes, you did.
I'm free.
You did
I'm off the
awesome. Please, a round of applause for Dr. Amin Aknok. Yes, he has done very well, and we enjoyed him. So, just before we close, we'll listen to a few announcements, and then we'll listen to Engineer Issa Binu, who would equally talk to us before we all go, and we'll resume here tomorrow. But before then, I'd like to introduce our second lead instructor for this training. He just came in. Please let us put our hands together for Engineer Dr. Patrick Amor Beko. I hope I tried. Now, he is a chief civil engineer with specialization in geotechnical, pavement structures, and transportation engineering. He is currently the vice president of Ghana Institution of Engineering. He is also the vice chair of the Education and Training Committee of the Engineering Council of Ghana. Let's put our hands together for him. So just to walk you through what we have done today. Today we've had the introduction to roadway network components. We equally talked on the parameters impacting road network conditions, resilience, and sustainability. And just now we ended with history of pavement design theories and their impact on roadway conditions. Tomorrow, the training begins at 9 a.m. prompt. Please, there is no, I don't want to call it African time. African time here is 9 a.m. Would be going through super pave and balanced mixed design, roadroid presentation on data collection techniques, advanced inspection techniques, advanced data collection, analysis, and visualization for efficient roadway asset management. Then we'll have open discussions, questions, and answers. I'm very sure by the time you get to the house and you go through your notes, you have a lot of questions to ask tomorrow. May I now invite Engineer Issa Binu, who would now wrap up the session, tell us one or two things, and then we'll call it a day and meet tomorrow morning. Thank you.
I think you want to give yourselves a round of applause. Thank you for today. We need to call it a day now. Tomorrow he has already given you the lineup of what you are going to do. Please note we are going to start 9. For throughout the whole of this exercise until Thursday, we will adhere strictly to the time we have laid, except if there's something that comes up beyond our control. Tomorrow we are going to have additional hands. Today we only had Dr. Amin speaking with us. Tomorrow Dr. Patrick will join. He just arrived not quite about an hour ago from Ghana. Also tomorrow we are going to have a Zoom connection with one of the experts from Thailand, also giving his own experience, roadroid experience in that regard. We have designed this program such a way that we will not just call it international on paper, it is really international. We should have international experience and share all the necessary, the latest in the industry. We want to make sure that our engineers, our experts are able to get access to it and you use it for the betterment of the work you do for Nigeria. Not to say much again, except to say thank you for today's patience. Please come early tomorrow and be sure that we are going to have to continue.
See, we have also international participants.
It's also good to note that all the resource people are varied all over the world. We have said Amit came from the US, Patrick is coming from Ghana, Mikhail will be talking to us tomorrow from Thailand. We also have amongst the participants, earlier in the day we were asking people from Federal Ministry of Works to put up their hand. We saw a large number. FEMA, we saw a large number. But we didn't end up, I think we ended up with Keystone Bank that were 2, but they are not the only ones that are 2. We didn't end up with, we have also international participants. We have people who came from other African countries to this program amongst us. Can I kindly ask the participants from Ghana to please upstanding for 2 minutes? They got the adverts. It's an international advertised program. They showed their interest, and today they are here in Nigeria to participate in exactly what we are handling. We hope as we go on, this hall will now be divided into West Africa, East Africa, North Africa, and so on. That is the aim, and I think we will achieve it. Thank you very much.
Thank you very much. I'm from Ghana. I hope you've eaten our jollof rice. Every time we'll be arguing with jollof rice, and it's the same rice. Oh. All right, thank you all very much. See you tomorrow by 9 a.m. Please do have a wonderful night rest. Bye.